Okay, so I'm Michael Blake, and I primarily do the interface design, and Ted does the processor stuff. And we'll let Ted introduce himself later. He's going to show you some complex examples. I'm going to show you ease of use and use a relatively simple example. In fact, this is just a block in IronCAD that's been resized to 5 inches by 2 inches by 1 inch. And I'm going to show you basically how easy it is to do multiphysics, multi-body simulations with multiple materials. I've already set it up with amps. Here's the multiphysics add-in here on the add-in bar. These are the toolbars that are used for multiphysics. The first step is to select Add FEA, and you can do that from the toolbar. And again, this is the analysis types. Three-dimensional static is the most common one. That's the default. We just click OK. This is the FEA docking bar dock. And the top part is a tree that summarizes the FEA model. And the bottom part is essentially, these are dialogues that correspond to whichever page the tree is highlighted. The units, well, okay, we'll get to the units. These question marks here are things that have not been looked at or have not been set, and you need to go through those to set them up for your specific FEA analysis. So we'll start at the top and work down with the question marks. The first one is the model page. This allows you to add new materials. It shows you the default units, and similar to IronCAD, these are essentially display units, so you can change these at any time. So we go in inch. It defaults to USA system and Fahrenheit because they used inch in their IronCAD model. We go check the materials. The default material is carbon steel. That's going to be fine for our example. Constraint. In doing a static example, typically you fix or hold one part of the model and apply some sort of force or load on another part of the model. So the constraint is what's going to be fixed, and we're going to fix it by setting the position to 0 for X, Y, and Z. So we do update entities here and use the key creator, the IronCAD trick here of the Control and Alt key, and click on this, select the back face. Oops, Control Alt, click on this, select the back. I have to move. Okay, select the back face, do accept, apply. So we've now fixed the back face. Now these little icons show that it's fixed in all 3 directions, and I cheat a little bit. There's right-click menus to a lot of these pages here, and I go up to model preference, and the default is 100 for the scaling size. I like to crank that up to 180 so they're a little easier to see. And another cheat I do from the default is I turn off the advanced results for experts so that I typically get the results options that that I'm interested in, and not a lot of them that I never use. So let me go ahead, and then I do save as defaults to save those. So right-click menus are available for several of these. Essentially, our whole interface is done by clicking on these right-click menus and this toolbar over here. So that represents, and plus the dialogues that come down here, represents the full interface. So we're done with constraints, ready to go to loads. That's the next question mark. We're going to add pressure. 100 psi is fine. We're going to update the face, select the top face, accept, apply that. The next category is mesh. We haven't done the mesh yet. We can add refinement to the mesh. If we have multiple parts, we can control whether or not they're glued together or they act as independent parts. When we're ready to generate the mesh, we click on this. This goes ahead and sets a default mesh size that's usually fine. There's other options here for changing the mesh. Basically, just hit generate, and it generates the mesh for us. Now we're ready to look at the results. We first need to analyze the model. This is the 8th FEA analysis program. It's all done already. We're ready to look at the results. There's this read new results, which is actually not used if you're typically doing only a one-step static analysis. If you're doing a complicated multi-step analysis, this allows you to look at intermediate results, all the completed steps, before the full finite element analysis is done. So for example, if you have a 2-hour analysis that does one time step every minute, after the first 10 minutes you can click on Read New Results, look at the first 10 time steps, and verify those, see if they're going, if it's going in the right direction, and if not, you can cancel it and start over again and save yourself, more than an hour and a half. So we're going to look at the animated scale, and again, we just click on that. This will scale the deflection from 1 to 465 times the normal deflection and animate it, and this is what we expected. We're holding this side, there's a pressure on the top. We can also add contouring. This is stress contouring, so we can see the stresses. I talked to you earlier about that advanced option. If you want to see all the options, if you click on this little advanced button, then go up to contouring, these are all the FEA options that are available for stress, which include nodal forces, the strains, the error norms, and all of those. If you don't have the advanced option on, then it summarizes them. Essentially, you get a subset that are the ones you typically use: the stress, the displacement magnitude, and the displacement in the various directions, and the strain. Okay. We can stop that. We also provide tools to look at any node and look at the value at any specific node. In some analysis systems, you have to specify which node you want to analyze, or which node you have to specify ahead of time which node you want to get information from. In ours, you can do that for any node. You do a node inquire, and we're on equivalent stress. We can change this pull down to something else like displacement magnitude, and we can get this position for any node anytime in the simulation. We can also introduce a cutting plane here and move that through our model to look at stresses throughout the model. The node inquire also works on nodes in the cutting plane. So as we move here, if it's an artificial node from the cutting plane, it'll have a negative node value. But then we can look at stresses individually and see them. Here's the actual value of the stress at this point in the model. So I'll go ahead and turn off the cutting plane. Let's see, we can do plots of various things. In multi-step analysis, you typically plot something as a function of time or a function of time step. This is a static analysis, so there's only one time step. So the best we can do is plot things. Let me see if I can select this. Okay. We're going to plot along a direction. So we're going to take all the nodes that are part of this line and plot them as a function of the x direction. We're going to plot the equivalent stress. So we click on the plot button, and here we see the equivalent stress. Essentially, it's multiplying it by this vector, which means this is the x-coordinate. So starting at about -2, going to 2.5. So we see the stress starts high and then gradually goes low. So that's some of the results properties we have. So that's a simple analysis. It took us just a little time to do. The next thing we want to do is show you how easy it is to do multiphysics. So we come back up here, and I'm going to copy this analysis, so we keep the copy the simulation, so we keep a copy of the other one. We could change the analysis type when we copy it. So this is just a copy of our previous one. We have 2 simulations down here. And on this one, I'm going to do a thermal analysis also. I'm going to fix this temperature at 0 and then set heat on this side. And the hotter material is going to expand more, and we're going to see a combination of both stress due to thermal expansion plus the solution of the thermal problem. And this is real easy in Multiphysics for IronCAD. On the analysis page, we just tell it we want thermal analysis. For each material that we want involved in the thermal analysis, we turn on its thermal analysis property. So the steel is going to participate in the thermal analysis. Typically, if you add a new analysis, you're going to need to add new boundary conditions. And as I said, we're going to have to tell it to fix the temperature on the back page, or on the back surface, and to go here, load. See, because we're doing thermal analysis, we have more options here. We're going to do a heat of 0.02 on the front face. And that is it. We've set up everything to do a combination stress and thermal analysis. We're down to the results. We click on Analyze. It's done. It performed both analysis at the same time on the same set of nodes to give us the most accurate results. We can go up here and do a contour display, go down here and check out the temperature. This is pretty much what we expect. 0 degrees here as we fixed the temperature to 0 degrees, and then it reached up to 57 degrees Fahrenheit here. If we do an animation scale, we can actually see the two motions in there. We can see it bending to the right because this part of the model is hotter, so it expands more. And then if we get it down here, we can see the top bending down due to the pressure that we put on top. So there's a complete multiphysics thermal static analysis done in just a few steps. The next thing I want to show is multiple materials. To do this, I'll turn off all our FEA stuff so that we can more easily access the IronCAD. I'll move in a cylinder here. I'll right-click on this and edit size box. This is my favorite command. 1.5. So this is going to be 1.5 inches in diameter, 2 inches high. Okay, use the trackball to point, and I'm going to put it right here in the middle, and then I'm going to move it 1 inch in this direction so that it's off-center. Okay, so now I have a model with another part. I can go over here and I can turn the FEA information and window back on, and essentially the FEA tree is the same. The only real difference is this Sync, Sim, and Part button is now turned on. So when I click on this button, it tells me I've added one new body, haven't removed any bodies. I click OK, and now it's added the new part to the FEA tree and added it under the existing material. So if I wanted just the same material, I could do the analysis now. Actually, I want to add a new material, so I go back here up to a little higher on the tree, add new materials. For category, I select non-ferrous. That gives me aluminum, which is fine with me. I go ahead and apply that. Once I've added the material, I have to add bodies to the material, so I click on Add Bodies, click on this top one, click on Accept, and Apply. And now I have carbon steel. If I click on this, it shows me Part 1 is carbon steel. This is highlighted here. Part 2 is aluminum. Part 2, and here's right there at the top. And because I've changed things, I have to remesh, so I get a question mark here by the mesh because it's not up to date. Again, go ahead and accept the defaults, ignore little error messages, and I'm doing fine. Now I can go ahead and analyze the results, and I can do an animation of scale. Here's a scale animation. I can, let's see, contour display, temperature. Okay, let me stop the animation. Actually, this is a little more interesting temperature results because the temperature diffuses in here. We get it close to the average temperature up here at the top, and so instead of just a linear temperature gradient across our material, we get a nice, and this affects the temperature on the underlying bar. So that shows the effect of adding new materials. We've now done a multiple part, multiple physics analysis. The one other thing I want to show you is we want to now make it a little more interesting by adding a force that goes around this cylinder. So an azimuthal force that goes around the cylinder there. We can do that by going to the load section. We want to add a force. We'll set it up for 2,000 pounds, pretty hefty force here. Select the surface to receive the force. And this force points out. We really want it in cylindrical coordinates, so we come down here, pick cylindrical, still points in a screwy direction. We need to set up our coordinate system. We can enter the origin, enter the direction, or we can get both the direction and origin from an arc in our model, which is what we want to do. And now we have it going out in the radial direction. We want it in the theta direction. We'll go to Set Direction, click on Theta to put all the components in the theta direction. This is going in the right direction, but let's reverse it and have it go the other way. So now we've added a force onto our model that's twisting this top cylinder. The results indicate that they're no longer up to date. We go down to the results, redo the analysis. We can do our animation of scale. And we see that due to the twisting here that it's changing it a lot. We'll do a contour display of the equivalent stresses. There's the equivalent stresses. Just one last thing to show you. Let's say we really want to see just the effect of the twisting. We're not interested in the pressure, the heat anymore. There's a quick way to right-click on these, as I said. Clicking on these, right-clicking on these, clicking on the toolbar, and the dialog down here, that's the only way to enter information into the FEA system, so it's actually a fairly simple system to operate. So we want to disable the pressure. We're going to ahead and disable the heat, so we're left with just the force. Again, we have to reanalyze. So then this gives us our previous system with just the force. We can do a scale animation. This is the result of just twisting. We turn on the equivalent stress and get an animation with the equivalent stress turned on and the model changing. So that's pretty much the demonstration. It's in just a few minutes we've done multiphysics, multi-material with various stresses and temperature and heat conditions. Thank you.
Thank you, Michael. I guess we'll go ahead and hand it over to Ted. Ted,
okay.
do you want me to share your screen?
Yes.
Okay.
Please. This is Ted. I am more involved with analysis, so we have given it Carrie a setup example problem to show you what can be done using this multi-physics for IronCAD. So the first example problem in the set that you're going to get is a very simple knob model, which is basically a twisting motion. Like Mike has demonstrated, that you apply a tangential force on this knob, and then the behavior is just very simple. The first time you do this, we try to make it simple for you. So this is the first example. So it's twisting, and that's pretty much the first exercise if you try to get a hands-on experience with IronCAD. So that's the displacement. So and we suggest that you start with this model to begin with. There's a detailed step-by-step information how to perform this analysis. Okay, so that's pretty much a simple model that we're going to demonstrate. Okay, let's start the second one. Let me see what you say something about. No. Okay, so the second model I'm going to show you is basically several dynamic analysis ability. The first one is basically it's called a model analysis, which is basically the natural frequency vibration. So if we turn on this one, you see this is the, let me see, let's go down to the lowest mode. This is this is the tuning fork. So the first mode of this one in this design, which is basically bad, which is basically vibrating in the lateral mode. The second mode of this one is actually the vibrating in the in-plane motion. That's you can see that the frequency of this one is 1900. The third mode of this one is the side swaying, opposite side swaying mode. You can see this frequency is 2200 roughly. Then going up, it's another in-plane motion, but it's now at the crossing each other. So this is the basic the natural frequency, or what's called a model analysis. Okay, so if you're designing this type of thing, you absolutely want to avoid this kind of operation frequency. Okay, so let's go to the next one called buckling. Buckling is basically that the material has enough strength, but if you lower the material beyond its at the buckling instability point, it's going to collapse. Collapse being that the shape of the material, the shape of the model changed dramatically. So in this case, it basically tells you that there is 84 times the buckling load factor. In this case is lowers the most 84 times of this to apply the vertical pressure. So it's going to buckle laterally. So if you're trying to do a support system like this, you want to prevent this kind of a lateral motion of buckling. So let me go to the next mode, which is basically this one. So the first buckling mode is lateral. So if you are trying to build a support system, you want to prevent that buckling shape from happening. So you have to do a lateral bracing. Okay, so that's called a buckling. The third type of a dynamic motion is called a frequency domain. So let's say you're vibrating this at the tuning fork at this at the loading, which is basically nothing but 1 pound. Okay, so what's going to happen is that if you happen to operate this load at the reaching the natural frequency of the tuning fork, okay, it's going to resonate, and the deformation is getting larger and larger. And if you do not prevent it from happening, it will eventually collapse the system. So let me just show you the animate of this guy. So that's at the end of the day, that's what's going to happen. And if you show, let me just plot the displacement of this guy versus frequency. So let's just plot displacement magnitude of this guy. So let me click on this guy, plot, select node history. Okay, so what you're seeing is this is the frequency of 7700, exactly the same loading, except you're changing the loading frequency. So you're vibrating this one. You can see that at the static, which only happened at 1 inch. But if you're reaching the natural resonance frequency, it's going to vibrate all the way up to 34 times. That's what's called a dynamic load factor. So basically, this is a dangerous situation in design, that if you, especially you have a vibration machinery. So you want to avoid this kind of a natural frequency. So this is crucial in lots of design. So in this option that we're using the frequency domain analysis to understand the behavior of the system loading under the dynamic ranging of frequency domain motion. Okay, that's the second model. So that's still very simple, simple linear elastic. The third one I'm going to show you is basically the coupled physics, which is basically a model engine. And so let's get down to the point that we select the stress and thermal just like Michael did. And let me show you the behavior of this one. What we're simulating is a combustion behavior of this engine in the inner piston, by we applying a heat flux on this interior face. Highlights green, so it's not showing up very well. So if you analyze this one, you can see due to the combustion behavior, you will have a temperature that is rising very quickly. And if you look at the coupled motion of the stress and thermal, this is the behavior, okay? And you can look at also the stress, which is basically the crucial in this design, equivalent stress. So that's equivalent stress because it's supporting it here. This is a hookup to the front of the airplane. So this is the part that you want to be careful when you bolt it to the wood, okay? So not much, but it's things that when you're designing parts, that's the thing that you're looking for. All right, so let's close this one. Let's go to the next examples. Okay, so this is a simple centrifuge. This also demonstrates what the multiphysics, the analysis that what we can do. What we're looking at is basically a spinning model, okay? And other than applying the regular constraint and everything, we're rotating this parts at 30,000 RPM, okay? And we want to see what's happening. So let's take a look at what's happening here. Let me turn on the mesh. Animate the scale. Okay, you can see that at the 30,000 RPM it's deflecting, and let's look at the maximum displacement, because that's crucial in design. So when you turn on the spinning or centrifugal loading, it will tell you the displacement in tangent or radial. And most of the design in rotor dynamics machinery, they are interested in the radial deformation. So you can see that it's about 0.2 millimeters. So it's very, very acceptable. Okay, so and you can turn on a cutting plan, which we recently added, allow you to examine the behavior of inside. Okay, and this is still very simple linear elastic analysis. So let's finish up this one. Let's move on to the next model quickly so we can save some time. All right, this is a little bit more complex, but it's a very simple model as well. This model is basically probably at this moment using the maximum physics that allowed. We haven't added the fluid yet. Right now it's using stress thermal electrode. This is basically a chip with the cooling fin attached. So this is a silicon wafer on this one, and this is basically the base material called tip base material with this component, which is basically a cooling fin. So basically what we're doing is we are applying by simplifying this circuit using basically the Joule heating, because we're interested in the thermal and the stress behavior. So basically we apply a voltage of a 12 volt standard operation for the chip. And we look at the first thing, let's look at let me turn off the mesh. So let's look at the voltage first. This is the voltage boundary condition. So we have a voltage applied from 0 to 12 volt here. And due to that, what's called a Joule heating, basically the chip is going to generate lots of heat. So let's look at the temperature. The temperature is up here. Okay, so this chip is engaging in cooling, convective cooling due to the fin. So you can see the behavior of this temperature behavior. And let me show you the stress behavior of this one. Okay, so that's how it works. And if you make a cutting plan across this guy, you can see the behavior of the temperature profile. Okay. Let me see if I can rotate this way. Yeah, much more interesting. So this is the temperature profile. And let me show you what other interesting thing that you can do. We can see the heat flow. This is all available vector plot or streamline plot that you available. Okay, depending on the physics that you have. So let's plot a streamline of. Okay, let me turn off this guy. Let me turn on the cutting plane. Let me turn up the model. So this is the heat flow of how the system from the heat generator to the cooling surface. Let me see, it might make it more meaningful. Let me change the density of this guy, maybe 3, less crowdy. Update streamline. Okay, so this makes much easier to see. Okay, so this is the heat flow from the chip to the cooling fin. So this is what you can do. You can also show the vector plot of the detail of how all the heat flux goes following the streamline to the surface. So this is probably right now the most complicated multi-physics that you can do before we turn on the flow. Then with the flow you can actually simulate the airflow through this. Right now the airflow is simulated using convective cooling. Okay, so that's it. Okay, so let's go on to the next model quickly. It's getting a little bit more multi-physics and more complex one. This is actually equivalent to the drop test. Pretty much you drop a bar to a ground, except in this case, we are not just dropping. We are accessoring this bar, which is basically a round cylinder metal, at the speed of roughly about 200 meters per second, almost like a bullet, okay, rather than a simple drop test. So the behavior of this one, the way that it goes, is like this. And by the way, this is a technically called Taylor bar. This is used heavily in the defense industry for checking the behavior of. So this is what's happening. That if you really drop the cylinder to the ground at this speed, that's what's going to happen. Equivalent stress. Okay, so and we can turn on the behavior up. Let me turn off the mesh. Let me show the velocity profile. You can see how the wave hitting when it hits the wall, it's basically the stress bounce back and then back and forth. We're looking at about I think 1 millisecond total of impact time. Okay, so yeah, this is effectively the penetration or the crash test effectively. Let me turn on this guy. So okay, so this is pretty much it. That's for this model. That this demonstrates. This is basically a plastic deformation that happened at the tip. So it flare out just like if you hit a BB gun ball against the wall. That's what's going to happen. Okay, so let's move on to the next model. Okay, the next model is actually a benchmark model from one of the customer. They are performing. This is a rubber material, and they are doing an experiment. The original intent. This is the blood vessel pushing against the tissue. A lot of time when both are very flexible material, pushing the steel bar against this too, it's very hard to say whether this will clog this band or not. So this is the behavior of this guy. Let me see where I can get the, yeah. Okay, so let me turn on the contour first, turn out the light. So let's see how it behaves. So if you squeeze it, okay, let me see where I can get anything better. So if you squeeze this at the technically incompressible rubber. Okay, let me hide this guy for you. So, oh, I'm sorry, I turned off that display. So if let me hide half of this guy, hide selected it. So you can see this one actually squeeze all the way into the system. So it stopped the blood flow in this case, and then squeeze against the tissue. So this is one experiment that they have done. They want us to duplicate this one in simulation for basically to understand the behavior of the blood tissue and human fat, I guess. So let's see, you can show the equivalent stress. So this is interesting behavior. If you run this to all the way up to against the wall, then it's going to run pretty much a long time, because it can keep pushing until it can no longer squeeze, which is basically the behavior in compressible material. Okay, so that's about it. Okay, so the very last example is pretty much the very interesting demonstration model of our contact technologies. So this is let me see. Let me turn out this. This is a pool game analysis. So this is modeled after a child pool table. Okay, so the behavior of this one is actually extremely realistic because it considers all the form material of the side, the close, the table, the table behavior due to the closing damping behavior, and then the rolling friction and the contact friction of the ball. So let's look at what's happening here. So if you turn this in, you can run this at yourself when you get this model, change the behavior of the impact cue ball speed, and this, let me just speed up a little bit so you can see what's happening. So let me speed up the display by twice. So you can see you knock one ball out of this at the game. So it's replay from the beginning. Okay, and let's turn on the show velocity, see how all the velocity goes. Okay, so that's pretty much all I want to show you of how the multi-physics for IronCAD can be used in solving engineering or design problems. Okay, so Gary, I think I'm done.
Okay. Just one comment. I just wanted to see if you could highlight on the advantages of having that automatically when you have multiple parts. The glue option. I don't know if everybody caught that. When you have that glue option, the mesh, when it's generated, it automatically knows how to continuously mesh between the two parts automatically for you without putting contact.
Oh yes, that's actually the simplest and commonly used. When you okay, for the groove parts, for example, if you come to here and you say groove parts, groove body, what you're saying is you want this at the pool table and then the four side to be basically glued together. Okay, now if you look at this outer parts, the pool ball, they are not in any one of this glue group. Okay, so they are meshed separately. So you can just basically simply say, okay, I want everything engaged in contact. That is an independent part. So that means the pool table side and the pool table, they will not engage in contact to each other, which is basically realistic. That's what's happening. But the ball will engage in contact with the rest of the ball, the table, and then the side. Okay, so that's basically, so the default behavior when you generate a mesh, they are glued. In this case, we're doing contact analysis, so we're basically saying generate a mesh, but generate them as the separate bodies, so you can engage the contact physics and then perform the analysis. Okay.
Okay. Thank you very much.
Okay.
Okay. I'll open up here into questions for a minute.